we are Team 7. Today, we're going to present our flood prediction tool. First, let me introduce our teams. This is our teams. And before I move into the details of our coding, I want to introduce our presumptions of prediction and softwares. First, for the prediction, we believe geological location is the key, which implies that same eastern and northern location should contain the same features. So if we face some different postcode with same eastern and northern, we just drop them. And for the software develop philosophy, we believe simple is better. If the single model can do it, we don't do it twice. It will help because less model means less training times. And we reduce our training model as much as possible. This is our class skeleton, which is very simple. We just take the provided data and add it with the extra data we research and combine them into a comprehensive data frame for our models. And if you input the model keys, you can just call your function and get your predictions.
So the overall goal of all of these classes and functions is to, at the end, gather multiple visualization methods in order to detect and predict different flood-associated risks. So in total, there's 8 machine learning models, 6 for the risk prediction, and 2 for price prediction of the house. So the folder structure is, we have in the document a folder containing package usage and model information. Then we have the scoring tests, and you can also test using custom tools to see if everything is working as anticipated.
So this is our first task. The task is use the OSGB36 location to focus the flood risk. So this is our my function. This means the rest 2 functions prediction from postcodes or latitudes and longitudes call this function. So before this, we need to do some data processing. And just as what we showed in this graph, if there are 2 postcodes, the return may be the same. We get the same northern and eastern, but through this function, we might get 5 different postcodes. So if we do not drop duplicates, we cannot set index of them. So in this test 1, we use a model called random forest classifier, and we also modify the weights because this is unbalanced data. So according to the scoring matrix, if a risk area is predict to the risk 1, then the score will decrease for at least 2,000. So we do this to get the better result. And we have run the test according to the dataset given by James this morning, and we get the very good accuracy, recall, and precision at 1 score. So the total score and of our model is very high. And this is test 2. I think it is very similar to the test 1. It's just called test 1 in this model, so I will not go very detailed into this. But we do a test, and the input is just the postcode list, and we get the good result. The test 3 is the same with the test 2. So just change the input as longitude and latitude, and we also get the result. So
in the development of our predict local authority model, we performed a grid search in order to find the best classifier for our problem. And as a result, we found out that KNN predicts the local authorities with a high accuracy, outperforming the other models. And we also determined that the best number of neighbors for our KNN model is 4. Then, using the KNN model, our function predicts the local authority from the easting and northing. And we also filter the data frame in order to find the postcodes corresponding to our input easting and northings. And finally, we output the series indexed by the postcodes. Our model has demonstrated a very good performance with F1 score of over 0.98. However, it could be improved even further by doing more hypertuning or ensembling our KNN model with some other classifiers. Now coming to the predict historic flooding. For this function, we did an extensive EDA and determined that soil type and elevation don't have a considerable impact on the performance of our model. That's why we simplified our dataset by removing those features, leaving only easting and northings. And in order to select our model, we did a randomized search with different classifiers, and consequently determined that the random forest is the best algorithm for predicting the historic flooding. Now, using the random forest model, our function predicts if the postcode was flooded before using eastings and northings. And as in our previous function, it outputs a series indexed by the postcodes.
Task 6 is about predicting the median house price given a sequence of postcodes. So the objective of the function is to take a list of postcodes and to return the median house price within that particular postcode. So we have two methods here, one that utilizes external data and one that doesn't. We're going to look at both of them, but the inputs and the outputs are the same for both. So again, for model selection, we tried linear regression, but that was giving bad results. Now, we firmly believe that's because of the low levels of correlation between the input data and the feature we want to predict. We also tried XGBoost, but we weren't able to create anything meaningful out of it. After this, we decided to use random forest as our main algorithm. To get the best results, we used grid search. Now, again, there are two methods for the user to choose from. The first one calls on external data, as we explained before. The second one doesn't have any external data and simply performs a merge on the datasets that are already present in the repository. So let's look at the external data because it's slightly more complicated in the way that it brings and merges data. The first step is to take the district and sector data and to combine it with the postcodes labeled data. We have annual income, which is an external data. We have the active DF, which is the number of people working actively in the industry in a postcode, and the employer rate, which is the number of the percentage of people that are employers. We remove unrequired columns, slash out the outliers, impute, scale, and then grid search for random forest. Now, for the second model, we don't do any of the external data merging, and we just do the steps we did before. However, since there's much less data involved in the second model, it gave us a lot of option to fine-tune the hyperparameters in more detail, simply because it was running quicker. And this gave us a much better RMSE score of around 47,000. And this is how the output looks like. So for a list of postcodes, send in as the input, which is PC here. We'd be getting a series with the postcodes as the index and the median value on the right, which is the value. Now, to predict total value, again, the input would be a similar sequence of postcodes or postcode sectors. However, for var code, we just coded on the postcodes and not on the sectors. A fully developed model was created by us to integrate for postcode sectors as well. But the problem with that was that it was getting too complicated and messy. So that would be a future improvement for another group that comes and takes this over. Let's quickly look at the function in a more graphical manner. So this is the data set we have. And then we divide the number of households by the number of postcodes. Then we multiply the median with the number of households per postcode. That gives us the total price per postcode. Of course, we don't need sector because we're doing it at the postcode level. Again, an improvement could make us add the sector later on, but not for now. Then the final data set would be the postcode and the total price per postcode.
And that's it. That's the result we want from this model.
So the next and final function is to predict the annual flood risk. So the input is a sequence of postcodes again, and this time the goal is to find the flood risk, which is calculated using the flood class and the total price of the houses in a specific postcode. So how do we find this flood risk? We first take the list of postcode and we're going to call two already made functions. So this model doesn't train and is very simple. First, we predict the flood class from the postcodes, and then we map the return flood class in order to get the flood probability. Then we do the same thing, but to find the total values of the house, and we get a data frame merged on the postcodes, which has flood probability and total house price. Now we can use this specific function, which has a weight of 0.05, to multiply the flood probability with the total house price in order to get the annual flood risk.
After retraining and fitting our models, we got 5 labels in total, which is flood class, median house price, historical, flood and total property values, and an annual flood risk. And here we can see that this is a comparison between the real data and predicted data of the risk label. As we can see that the result is good in some areas. And here's the median price. As we can see that we have 3 layers in the label data and 5 layers in the predicted data. And you can click the different layers by clicking this button. And here's our historical flood of the real data and predicted data. And you can explore more by going through our data visualization notebook.
And for the data visualization part, after 2 steps, which is the step 1 data acquisition and step 2 data collation, we can do the data analysis. Data categorized into rainfall, river level, and tidal level, flood risk assessed and classified as light, moderate, heavy, or violent based on intensity factors. By these 3 methods, we can finally draw maps and data. Following maps visualize UK flood risks from rainfall, river, and tidal levels. Users can switch layers and use an interactive time bar for exploring risk distribution at different times. And we can see 2 figures showed on the screen. Which one is a typical day flood risk map produced by local data, and another one is a chosen day, which is November 22 flood risk map produced by live data. And we can compare these 2 figures. We can see with the local data, the flood threat areas of live data are more and more concentrated. For flood threat prediction, the more concentrated distribution means the higher the accuracy of flood threat.
So overall, we get a model that manages to predict, and we manage to visualize all the major flood risks and different metrics that are useful in order to prevent any disasters. But there are still many ways that to improve what we did and for a future team to take on. Firstly, and perhaps most importantly, is to improve the model scores, which is especially the case for predicting the house price. So for instance, trying to find better hyperparameters or even better models and doing better EDA to really understand the data and maybe even find external data. Then we can also try and improve the robustness. So we mentioned before trying to get the total price function to work at a sector level as well, rather than just a postcode level. And finally, we can also try and make better visualization. So by adding, for example, more layers or having a better live map that would update. And yeah, thank you.